Hello, I'm Olivier Depré, technical lead on the Hafnium project. I'm happy today to co-present with Joa Alves about the Secure Partition Manager on Arm Cortex-A. We are both from the Arm open source software Trusted Firmware-A team, and we are both maintainers for the Hafnium project in trustedfirmware.org. So today, as an agenda, I will present a brief about the SPM roadmap, present and future, and we'll have technical discussions around those topics. So the introduction and the evolution of Secure EL2 partitions, what's new about the newly released FFA-v1.1 features. Joa will detail the notifications feature that is under work, and he will also talk about the recent improvement around the Hafnium CI. And as part of the technical discussion, there will be a brief about Arm CCA and the impact to the SPM. A bit of a recap about the software architecture. So you are encouraged to refer to the earlier presentations we made in 2020 and 2021 for the Spring Linear Connect, giving the rationale and the background for this architecture. In brief, our team delivers the secure monitor firmware in form of the Trusted Firmware project, and this SPMC component being the Hafnium project at S-ELO2. So that's an open source reference software stack to whom partners can contribute. So in this picture, you see on the right-hand side different flavors for secure partitions acting as virtual machines in the secure world. So this can take form of a legacy trusted OS managing TAs, or a bare metal platform driver at S-ELO1, or so-called S-EL0 partitions. So either in the present flavor using a shim layer at S-ELO1, or in the future by leveraging the virtualization host extensions in the secure world. So about the SPM roadmap, what we delivered in 2020 and is available upstream is so the open source reference EL3 plus S-ELO2 SPM, and which is demonstrated in the total compute software stack available publicly. In this release, there is the implementation of the handling of non-secure interrupts occurring in the secure world, the so-called manage exit feature, hardening around pointer authentication and BTI, the support for SAMD and SV context-7 restore, the support for the Arm IP, the Arm SMMU IP, and the associated driver at S-ELO2. Support for hot plug power management on and off for each physical core. The support for S-ELO partitions using the shim layer. We delivered a threat model for the SPMC, and we are applying as a continuous work fixes to support the FFA-v1.0 compliance. So what's under development are now incremental features to support FFA-v1.1 with an emphasis on notifications and secure interrupt handling, mainly because we ought to integrate Trusty as a secure partition on top of Hafnium and requiring those features. We plan some more hardening work around supporting memory tagging extension. As said, the support of S-ELO partition through VHC and improvements to the build system. And as of planned features, we intend to continue and complete the support for FFA-v1.1 with updates to setup and discovery features, the introduction of indirect messaging in the secure world and guidance around the SMMU, and the impacts of the legacy RAS and SDI, plus the newly introduced Arm CCA to the SPM. So briefly about S-ELO partitions, that's the today's architecture using a shim layer at S-ELO1. The secure service running at S-ELO can originate from the Arm Trusted Services project or from the standalone blob from the EDK2 code base. In general, such partition has a single vCPU which migrates across physical CPUs. And so the S-ELO1 shim layer was really meant for an initial enablement with FFA-v1.0. In reality, that's still an S-ELO1 partition, which embeds an S-EL0 application. And we observe some friction to the adoption of the 1.1 FFA specification, and hence the desire to migrate to a new architecture, which is this one, leveraging VHC in the secure world. So it was designed mainly for server use cases, but nothing precludes the usage in the mobile space. So secure services are host applications, and in that case, the SPM acts as a thin FFA trusted OS, managing secure EL2 partitions. And an interesting property that S-ELO1 and S-EL2 partitions can coexist in the same system. And also importantly, that's a partner contribution. Have a look at the TFA Tech forum, for which the link is provided at the bottom of this page. About secure interrupts, ongoing development. This is a catch-up to FFA-v1.1, implementing partition runtime models and the guidance for interrupts. As shown in the picture, secure interrupts can occur while the normal world runs and are brought to EL3, or while the secure world runs and are brought to the SPM at S-EL2. The geek hardware is owned by S-EL2 in that case. And we split this work into a phase one, where a par-virtualized interface to the geek is implemented, and migrating then to a phase two work where the architected geek virtual CPU interface is used. You're going to find the patch set through the link provided at the bottom of this page. And briefly, what is the Arm CCA impact to the SPM? So same picture, but adding the real world on the left-hand side. So eventually that's a four-world isolation. We expect a limited intersection with FFA, but the main changes are that the SPM has to call into the granule transition service for FFA memory sharing operations and for the SMU driver. And we also have the use case of a secure interrupt preempting a realm and the handling done in the secure world. Please refer to the presentation from Sodi and Dan about the Arm CCA and to gather more details in the same linear connect form. And now I'm handing over to Joa to detail the work done on the FFA-v1.1 notifications.
Hello, can you see my screen?
Yes.
Hello, so I'm pleased to be talking to you about the FFA-v1.1 features we've been working on. This slide serves as a quick recap on how the architecture currently looks like. On the following slides, we assume the presence of VMs in the system managed by an hypervisor and a set of SPs managed by an SPMC. Now, talking specifically about notifications. Notifications are a communication mechanism with non-blocking semantics as defined by the spec, are akin to a doorbell between two FFA endpoints and allow for two endpoints to progress with their workloads concurrently. The spec defines two types of notifications: per virtual CPU notifications, which are targeted to be handled within a specific virtual CPU, or global notifications, which can be handled by any virtual CPU, and this is determined by the scheduler. Notifications are signaled through interrupts. The spec defines two interrupts: notification pending interrupt, which is to be handled by the receiver when it has pending notifications, and schedule receiver interrupt, which is to be handled by the scheduler of the system when other FFA endpoints have notifications pending and they need CPU cycles to handle them. The support of notifications is enabled on the respective partitions manifest for each partition. This is still under work, and you can find the progress on the link in this page. So now let's have a look at an example signal flow. Let's consider the following simplified stack, where we have a primary scheduler, and then we have SP1, which will signal a notification to VM1. Normally, an hypervisor keeps track of notifications from VMs to VMs, and the SPMC is in charge of keeping track of notifications from SPs to SPs and from SPs to VMs. So in this case, the calls will be issued, some of the calls will be relayed from the hypervisor to the SPMC to update the status. We will also talk about the schedule receiver interrupt on the signaling flow. It's going to be handled by the primary schedule. At initialization, by default, it was a secure SGI that we've configured as a non-secure, hence thus donating it to the normal world. It is expected that in the system, the primary scheduler registers a handle for it. These are the interfaces that we'll be using through the examples in the subsequent slides. So FFA notification bitmap create and destroy are complementary interfaces. They are intended to be used by the hypervisor. The first is to be used by the hypervisor to allocate bitmap, the notifications bitmap within the SPMC, and the other one is to deallocate it. Then we have FFA notification bind, which is used is intended to be used by the receiver to give permissions to the sender to use a set of specified notifications. FFA notification unbind is to revoke those same permissions. Then we have FFA notification set, which is intended to be used by the sender to set notifications for a receiver. Then we have FFA notification get, which is intended to be used by the receiver to retrieve any pending notifications, and FFA notification info get, which is intended to be used by the primary scheduler to obtain a list of the FFA endpoints with pending notifications. Let's now have a look at a set of flow charts. So at this stage on this flow chart, both the SPMC and SP1 have been initialized. We are now going through the hypervisor's initialization. This stage, it might be that the hypervisor uses the FFA notification bitmap create in order to allocate the bitmap for VM1. This call is going to be issued to the SPMC, which is going to allocate the bitmap for VM1. If all goes well, it should return FFA success back to the hypervisor. The hypervisor should continue with initialization, eventually boot VM1 for initialization as well. This might be the time at which VM1 will use FFA notification bind to give permissions to SP1 to use a set of notifications. At this point, with this interface, the sender should configure the notification as being global or per virtual CPU. The hypervisor should, on its turn, forward this call to the SPMC, which should bind the notifications in a map to the specified sender. If all goes well, it should return FFA success, which will eventually get to VM1 as well. So at this stage, the SP1 is allowed to use FFA notification set interface. There are two uses for two configurations that may affect the way in which the schedule receiver interrupt might be triggered. So the sender might choose to delay the scheduled receiver interrupt or not have any no delay. In such case, the scheduled receiver interrupt should be masked upon the call FFA notification set. So SP1 effectively makes the call. The SPMC validates that the notifications are bound, fetches the bitmap from the receiver, and sets the notification as pending. As we don't have a delay in this case at the moment, it should mask the scheduled receiver interrupt and return FFA success to SP1. Because the scheduled receiver interrupt is a non-secure interrupt, as we configured it at initialization, we should go through the manage exit process. For this, the SPMC should have masked an interrupt as well, called the manage exit interrupt, that the SP1 should have handled and do any backup tasks before giving back execution to the normal world by calling FFA direct message response. The SPMC should detect that manage exit is ongoing and then save the status of SP1, unmask the manage exit interrupt, and forward the FFA direct message response back to the hypervisor, which will relay it to the primary scheduler of the system. At some point, the primary scheduler of the system should be preempted by the scheduled receiver interrupt. Alternatively, when calling the FFA notification set, the SP1 could have specified to have a delay on the scheduled receiver interrupt. And in such case, it would happen as follows. So SP1 would call FFA notification set. The SPMC would again validate that notifications are bound and fetch the bitmap from the receiver and set notifications as pending. If all goes well, it should return FFA success to SP1. SP1 would continue with its workload. Eventually, it would call FFA message wait when it has anything else to do. So the SPMC at this stage should give back execution to the normal world. It should, before that, check that notifications are pending and should mask the scheduled receiver interrupt. After, should relay FFA message call to the hypervisor, which would relay it to the primary scheduler, which would eventually be preempted by the scheduled receiver interrupt. So let's see now how the notifications are handled. So from the point in which the primary scheduler is preempted by the scheduled receiver interrupt. So the primary scheduler receiver interrupt arrives at the primary scheduler execution. When handling it, the primary scheduler is expected to call FFA notification info get. The hypervisor would relay this call to the SPMC. The SPMC would see that the VM1 has notifications pending, prepare a list with VM1 IDs. If all goes well, it should return FFA success, providing the constructed list. The hypervisor may append any other VM IDs if there are other pending notifications. For this case, the list will only contain the ID of VM1. If all going well, return FFA success to the primary scheduler. The primary scheduler will process the list, and at this stage, it should give CPU cycles to the partitions in need. So at this stage, it will use, on this example, it will use FFA direct message request to VM1, providing a specific payload so that VM1 knows it has a notification pending. This is an implementation defined way that we have as an example, just because with the current state of implementation of the notifications feature. So the VM1 would receive the direct message request, call FFA notification get, providing through its flags that it should retrieve pending notifications from SPs. The hypervisor would relay this call to the SPMC. The SPMC would retrieve any pending notifications, reset their state, and if all goes well, return FFA success with a constructed bitmap back to the hypervisor, which would relay it to VM1. At this stage, VM1 could handle notifications. This last stage of the flow might change in the future once we support the notification pending interrupt as well. Let's now have a look at the current state of the Hafnium CI. So the Hafnium CI is an in-source test infrastructure developed by Google at the time they were using Hafnium as an hypervisor. Because it's an in-source, you can find test source code and build artifacts for the test VM images in the Hafnium repository. So, and the testing setup you would obtain with what Google done was something as seen here in the picture, with a primary VM controlling issuing service requests to a secondary VM, and they would test the implemented functionality. In order to execute these tests, you can in Hafnium you can find the test.sh script, which basically specifies the test VM payloads that the HFTest Python script should use. So this script would, in its turn, spawn testing platforms loading the respective test images. It would grab the log output and organize them in the file system and determine the test results. On our update, we pretty much extended the current framework. We're using as much as possible what was already implemented, and in order to provide the SPMC support, then extending the testing setup to a more complete setup, including SPs and the SPMC. So we've added build artifacts to generate test SP images, and we added a specific shell script to specify the SPMC tests. Everything else just works the same. The intent in doing this update is to stress test FFA v1.1 functionality, validate interoperability between hypervisor and the SPMC, and complement any other tests that we've been doing to Hafnium with the TFA CI. The Hafnium CI is still a work in progress. We intend to use to keep improving it and make some changes to help with test scalability for the SPMC. That's all from my end. So thank you very much for listening, and we're open to questions now.
Thank you, Ja, and don't hesitate to ask questions through the Hafnium and Trusted Firmware mailing list. Thank you for your attendance.